This lecture is all about common gate amplifier working at low frequency band. I'll explain the performance of common gate amplifier at low frequency band and will derive the expression for lower 3 dB frequency for common gate amplifier at low frequency band. I refer my earlier lecture number 12 for the development of a small signal equivalent circuit for common gate amplifier at mid frequency band and for the derivation of overall voltage gain of common gate amplifier at mid frequency band. Let us start with the characteristics of common gate amplifier. It is non-inverting type. There is no phase reversal between input and output signal, and it has low input and high output resistances, and there is little signal current attenuation at the input. This is because of the second point, and it has unity current gain. That is why it is better known as current follower, and this has application in cascade system. As far as circuit is concerned, we are using single stage MOSFET amplifier, and coupling capacitors are CC1 and CC2 for the connection of input voltage source and load resistor. These are coupling capacitor, and there is one bypass capacitor CG. This is bypass capacitor, and there is no body effect. We assume that body and source terminals are interconnected. At low frequency band, internal capacitors CGS and CGD are behaving as an open circuit, but these coupling capacitors and bypass capacitors, they don't behave as a short circuit. That is why at mid frequency band, gain starts falling, and this is the rate 20 dB per decade. At lower 3 dB frequency, gain falls by 3 dB. At low frequency band, the whole circuit of common gate amplifier exhibits the properties of first order high pass filter, which can be represented by a very simple circuit where capacitor is in series and resistor is in shunt position. And this is the transfer function of voltage gain for first order high pass filter. And from this expression we can write the expression for lower 3 dB frequency for first order high pass filter. It is very simple. 1 by RC is equal to omega L. Omega L is the lower 3 dB frequency. On the next page, I'll explain a small signal equivalent circuit for common gate amplifier working at low frequency band. This is a small signal equivalent circuit for common gate amplifier working at low frequency band. These two are coupling capacitor, and this is bypass capacitor. This is input voltage source. This is the internal resistance of input voltage source, and this is biasing resistor, and this is drain resistor. This is the load resistor. This is the output, and this is the gate resistor, and this is voltage control current source, and R0 is the output resistance of the device. Since there are three capacitors, they contribute one frequency dependent factor in the expression of transfer function of overall voltage gain for common gate amplifier at low frequency band. That is why there are three lower 3 dB frequencies corresponding to these three capacitors. On the next page, I'll explain one method known as short circuit time constant method for the determination of one effective lower 3 dB frequency for common gate amplifier at low frequency band. And on the next pages, I will explain the effect of these three capacitors separately. For the determination of pole frequencies for common gate amplifier, we can use S-domain analysis, but S-domain analysis becomes tedious with number of capacitors involved. I'll explain one new method known as short circuit time constant, which is also very useful when we are not sure about dominant pole frequency and relative position of other pole frequencies. This short circuit time constant method approximates any high pass network of higher order into first order network where only one effective lower 3 dB frequency can be defined for quick analysis of the behavior of any amplifier at low frequency band. Let us start writing the transfer function for the overall voltage gain of common gate amplifier having three pole frequencies. So this is the expression for transfer function 3 pole high pass network, and these are 3 pole frequencies corresponding to these three capacitors. This one is for coupling capacitor CC1, this is for bypass capacitor CG, and this is for coupling capacitor CC2. and at lower 3D frequency the denominator should be equal to root 2. Just opening and considering this denominator is far greater than this numerator, this denominator is far greater than this numerator, and this imaginary term will be unity when denominator is equal to numerator. This is the condition, and this is called effective lower 3D frequency, and this is in fact sum of these three pole frequencies corresponding to these three capacitors, and in fact the sum is equal to the sum of the reciprocal of the time constants corresponding to these three capacitors, and we can write this expression in terms of Hertz also. So this is again effective lower 3D frequency FL in terms of Hertz, and 1 by 2 by sum of reciprocal of time constants corresponding to CC1, CG and CC2. There are three capacitors, so three steps are involved in the determination of time constants. In the very first step, we have to select one capacitor out of these three and consider other two capacitors as short circuit. For example, I am selecting this and considering these two as short circuit. Now I'll find out the resistance seen by this capacitor or the Thevenin equivalent resistance across the terminals of this capacitor. Then I will write time constant for this capacitor. This is the expression. In the second step, suppose I select this one, then I will consider these two as short circuit. I'll find out the resistance seen by this capacitor, that is RCG, or this is also called Thevenin equivalent resistance across the terminals of this capacitor. So this is the time constant. And in the third step, suppose I am selecting this one, this capacitor, and considering these two capacitors short circuit, and I'll again find out the resistance seen by this capacitor. This is RCC2, or this is also called Thevenin equivalent resistance across the terminals of this capacitor. We can write time constant for this capacitor also. After writing these three values, time constants for these three capacitors, we will be in a position to write complete expression for effective lower 3D frequencies for common gate amplifier at low frequency band. On the next pages, we will be determining these time constants separately for these capacitors. As per short circuit time constant method, and step number 1, I am selecting this coupling capacitor CC1 and considering these two capacitors as short circuit, and I am neglecting this R0 because this has got very high value, and when this is short circuited, G points comes here and this part is eliminated, and there is a plane, and looking through this plane toward the load, the total resistance is equal to 1 by Gm. This is equivalent to the total resistance of this part of the circuit, which has been replaced by this resistance. So this part is replaced by equivalent resistance 1 by Gm. Now I have to find out resistance seen by this capacitor, coupling capacitor CC1. I have to use Thevenin theorem. I have to replace this capacitor by a test voltage and putting this value equal to 0, and reducing this whole circuit into a simplified circuit. This is test voltage and this test current, and this is a parallel combination of RS and 1 by Gm, and through this loop current passing is equal to Vx divided by total resistance in this loop, and we can write Thevenin equivalent resistance for CC1, or the resistance seen by this capacitor CC1 is equal to Vx by Ix and Rs plus the parallel combination of Rs and 1 by Gm. From this expression we can write time constant for CC1, that is RCC1 into CC1, and this is the expression. In the next step, and step number 2, I will select this capacitor and will consider these two as short circuit. In step number 3, I will select this and will consider these two as short circuit. On the next pages, as per short circuit time constant method, and step number 2, I am selecting bypass capacitor for the determination of its effect and will consider coupling capacitor CC1 and CC2 as short circuit. So to study the effect of bypass capacitor, only this part of the whole circuit is useful, and from this circuit we can find resistance seen by bypass capacitor CG or Thevenin equivalent resistance for Cg, that is equal to RCg, it is equal to Rg, and time constant for Cg is RCg into Cg, that is Rg and Cg. This is very simplified circuit, and on the next page under step number 3rd, I will select this capacitor and I will study the effect of this coupling capacitor Cc2 and will consider these two as short circuit. As per short circuit time constant method and step number 3rd, I am selecting this coupling capacitor Cc2 for the determination of its effect and will consider these two as short circuit. Only this part of the whole circuit is useful for the determination of the resistance seen by this coupling capacitor Cc2, and from this loop we can write Thevenin equivalent resistance for Cc2, that is equal to Rcc2 is Rd plus RL. And now time constant for this coupling capacitor Cc2 is Rcc2 and Cc2, that is Rd plus RL into Cc2. So far we have determined the time constants for both the coupling capacitors and bypass capacitor. Now we are in a position to write complete expression for effective lower 3 dB frequency for common gate amplifier at low frequency band, just on the next page. Effective lower 3 dB frequency for common gate amplifier is defined as FL is 1 by 2 pi. This is the sum of the reciprocal of the time constant corresponding to these two coupling, and this is for bypass capacitor. We have already derived the expression for time constants corresponding to these capacitors, and these are the expression for time constants. So this is the final expression for effective lower 3 dB frequency for common gate amplifier at low frequency band. So this was all about the performance of common gate amplifier and the derivation of effective lower 3 dB frequency for common gate amplifier at low frequency band.